In today's lecture, we'll be covering main group chemistry, specifically the S block. The S block is comprised of groups 1 and 2, otherwise known as the alkali metals and alkaline earth metals. Group 1 includes hydrogen as well as the alkali metals. So that's hydrogen, lithium, sodium, potassium, etc., etc. Their general electronic configuration is noble gas NS1. The only exception is hydrogen, which is simply 1s1. The alkali metals have low ionization energies, low electron affinities, and low electronegativities, which means they're very good reductants. We will go through the general reactivity of alkali metals, but hydrogen will be treated on its own because of its unique chemistry. What do you think is the most common oxidation state for alkali metals? The correct answer is +1, but a simple answer like that won't be enough in this course. Memorizing facts without understanding why is just not enough. Your explanation will always need to answer the why in this course. So why is +1 the most common oxidation state for the alkali metals? Because they achieve a noble gas electronic configuration when they lose an electron. Group 2, on the other hand, contains the alkaline earth metals. These include beryllium, magnesium, calcium, etc. Their general electronic configuration is noble gas Ns2. And very similar to the alkali metals, the alkaline earth metals also have low ionization energies, low electron affinities, and low electronegativities. So they are also very good reductants. Additionally, beryllium will be covered separately from the rest of group 2 because of its unique chemistry. What do you think is the most common oxidation state for the alkaline earth metals? The most common oxidation state is +2 because the loss of 2 electrons gives a full valence shell. Starting with hydrogen, it is the simplest atom with 1 electron and 1 proton. In its elemental form, hydrogen is a diatomic gas. Hydrogen gas has a reduction potential of 0, and the reduction of protons at pH 0 acts as the reference for all standard reduction potentials. What does that say about the reactivity of hydrogen? This means that hydrogen can act as both a reductant and an oxidant depending on the reaction. It tends to act as a reductant more often, though. In this reaction, hydrogen is being oxidized by chlorine to produce hydrochloric acid. In this second reaction, hydrogen is being oxidized by oxygen to form water. This is the reaction that occurs when you burn hydrogen in air. The interesting thing about a hydrogen flame is that it is pretty much colorless if the hydrogen is pure. Sometimes you can make out a faint blue color at the base of the flame, as shown in this graphic, but this makes hydrogen flames very dangerous because you can't really see them. In this hydrogenation reaction, it looks like hydrogen is acting like a reductant, but the important thing to note is the palladium catalyst. If you look at the mechanism of this reaction in more detail, the hydrogen actually oxidizes the palladium, and then the palladium hydride intermediates that are produced reduce the alkenes to alkanes. Lastly, in this final reaction, lithium is oxidized by hydrogen to generate lithium hydride. This shows just how reducing the alkali metals really are. Deuterium and tritium are isotopes of hydrogen and are often called heavy hydrogen atoms because of the presence of 1 or 2 neutrons in the nucleus. Deuterium is used in multiple applications, including NMR spectroscopy and in kinetic experiments. We will not cover the kinetic isotope effect in this course, but it is important that you have at least heard of it so that you can research it on your own if you need to. Tritium, on the other hand, is radioactive and is used in radio tracing and pharmaceuticals, among other things. Other than 0, what is the most common oxidation state for hydrogen? The answer is +1. What is unique about hydrogen in this oxidation state is that it is a bare proton with no electrons. If you look at a hydrogen atom, however, its ionization energy is very high, much higher than the rest of the alkali metals. It is actually comparable with oxygen, which is a very electronegative atom. What this means is that bare protons on their own are very high in energy and don't exist under normal circumstances. Hydrogen bonding is a unique feature of hydrogen chemistry that is responsible for many phenomena encountered in both chemical and biological systems. It is unique to hydrogen because of its larger electronegativity in comparison to the other alkali metals. Because of hydrogen's relatively high electronegativity, it tends to form covalent interactions as opposed to the ionic interactions that the alkali metals tend to form. I said relatively high electronegativity for hydrogen only in comparison to the rest of group 1. Many main group elements are more electronegative than hydrogen. Some are so much more electronegative that they can polarize a covalent bond with hydrogen and pull away a significant amount of electron density. One example of this is hydrochloric acid. So much electron density is pulled away from the hydrogen that a significant partial positive charge builds up on the mostly bare hydrogen nucleus. This allows the hydrogen nucleus to form interactions or hydrogen bonds with electronegative atoms with lone pairs, such as oxygen as shown here. These interactions are actually fairly strong and can be up to 40 kcal per mole in strength. Multiple hydrogen bonds can have an additive effect and lead to very significant intermolecular interactions. This can have important effects in reactions, and this is also how DNA strands stick together. Also, it's very important in protein chemistry. Hydrogen atoms in the +1 oxidation state are also often used as catalysts, especially in organic chemistry. This usually takes the form of a proton from an acid, where the proton acts as a Lewis acid to pull electron density away from functional groups to make them more electrophilic. I'm sure you can probably think of many organic reactions that are acid catalyzed, but the example I will show you is an acid-catalyzed ester hydrolysis. So here is just an ester. And if you have an acid, this lone pair can attack the acid and get protonated. This forms a positive charge on the oxygen, which makes this carbon much more electrophilic. And then if you have water around, it can attack this carbonyl group, and generate this intermediate here. And then if you have a proton transfer, so from here to here, you can generate a species that looks like this. And this makes this group a much better leaving group. So when you reform your CO double bond, you generate your acid. And then at the very end, you reform your initial acid, and then you have your hydrolyzed ester, which is now carboxylic acid. There are many examples in organic chemistry of acids acting as catalysts in this way. Unlike the rest of the group, hydrogen can also support the -1 oxidation state and form what are called hydrides. The reason for this is that the 1s2 electronic configuration gives a full valence shell, much like helium. The electron affinity for hydrogen is fairly low though, around -73 kilojoules per mole, which is comparable with phosphorus. In addition, the hydride anion is disproportionately large. It is comparable in size to the fluoride anion, which has 8 electrons and 7 protons. Why would the electron affinity be so low, and why are hydrides so large? The reason the electron affinity is so low is because of the pairing energy in the 1s orbital. The reason hydride anions are so large is because of the repulsion in the s orbital and a low effective nuclear charge. One way to think of this is that the hydride anion has the largest ratio of electrons to protons of all anions. It's 2 to 1. All other anions have much smaller ratios, so the valence electrons experience a larger effective nuclear charge. With only 1 proton to 2 electrons in hydride anions, that's why they're so large, and that's also why they're so polarizable. As such, they are often considered soft Lewis bases. Highly reactive hydride salts form with the s-block metals, except for beryllium. Generally, hydrides act like bases and generate hydrogen. In the reaction below, you can see that lithium hydride reacts with water to form lithium hydroxide and hydrogen gas. Base is in quotations here because this is technically a redox reaction because hydrogen gas is produced. So you're going from -1 for a hydride to 0 in hydrogen gas, and you're going from +1 for hydrogen in water to 0 in hydrogen gas. You can think of this reactivity, however, as the hydride deprotonating the water, similar to a normal base. In fact, most hydrides only react with protic substances to generate hydrogen gas in this way. Also, the larger the cation for your hydride, the more reactive the metal hydride will be. Group 13 metals also form hydridic species, but they're more covalent in nature and generally less reactive. So these include boranes, borohydrides, and aluminum hydrides. Although they can react with protic species to produce hydrogen gas, these group 13 metal hydrides are much less base-like and can transfer hydride equivalents to reduce things like ketones to alkoxides, as shown here. The s-block hydride salts can't do this type of reactivity. They would generally form an enolate through the deprotonation, if you will, of one of those CH3 groups on acetone. Now moving on to the rest of group 1. The alkali metals in their elemental forms are soft, pliable metals that have low boiling points. They are so soft you can actually cut them with things like scissors or butter knives. They are very reducing in their elemental forms in the zero oxidation state, with reduction potentials between -3.04 volts to -2.71 volts. Note the large difference with respect to hydrogen, which is why hydrogen is such a big outlier. The alkali metals are so reducing, actually, that they react with protic sources to generate hydrogen and the corresponding conjugate base salt. So shown here is a reaction between an alkali metal and water. And you can see the color that's forming in the solution is simply a phenolphthalein additive, which is showing that the solution is becoming more basic. They are also reducing enough that when they're dissolved in ammonia, they will freely release an electron without an external oxidant. This forms really neat blue solutions where you have solvated electrons, and these solutions will slowly decompose over time to give amides as well as hydrogen gas. So this really shows you how reducing the alkali metals are. The only other oxidation state adopted by the alkali metals is +1. In this oxidation state, they form small localized charges and are considered very hard Lewis acids. As such, they form mainly ionic species, which you are probably familiar with. Some examples include lithium chloride, sodium chloride, potassium hydroxide, etc. Almost all ionic species with alkali cations are soluble in water. And the alkali cations can also act as Lewis acids in place of Bronsted acids in many organic reactions, due to how charge dense these cations actually are. They can be used to withdraw electron density similar to H+. When talking about alkali cations, it is also important to talk about crown ethers. These are macrocyclic ethers that bond alkali cations quite strongly. Depending on the size of the crown ether, the bonding pocket will selectively interact with different alkali cations. The larger the crown ether, the larger the cation bound. If the ring is too small for the cation in question, it can still interact with the crown ether, but it will generally sit above the plane of the macrocycle. Crown ethers are named according to their ring size and the number of oxygen atoms. So this smaller crown ether has a total of 12 atoms in the ring and it has 4 oxygens, so its name is 12 crown 4. At this point, you should be able to name the other crown ether on the right. So its name is 18 crown 6. Crown ethers are important because they can help solubilize ionic compounds in organic solvents. Somewhat similar compounds are cryptands, which are three-dimensional polycyclic molecules. A common structure is a polycyclic ether with nitrogens at the ends, as shown here. Depending on the size of the cryptands, they can bind different alkali cations in their central cavities. Unlike crown ethers, however, cryptands have a variety of naming conventions, just one of which is shown below. Using this convention, the cryptand on the right would be 222 cryptand. Notice that the nitrogen ends are not considered donors, it's just the oxygen moieties. The biggest difference between crown ethers and cryptands is the cryptands completely encapsulate the bound cations so that they cannot interact with anything in solution. Crown ethers, on the other hand, allow interactions above and below the plane of the macrocycle. Sometimes it is important to completely remove alkali cations because you don't want them acting like Lewis acids. In those cases, you would use a cryptand. If, however, you still wanted that Lewis acidic reactivity of your alkali cation, you would use a crown ether. Now moving on to the alkaline earth metals. They are similar to the alkali metals, except they are strong 2-electron reductants and not just 1-electron reductants. Why might this be? Because they need to lose 2 electrons to adopt a stable noble gas electronic configuration. In addition, similar to the alkali metals, they form soft, pliable metals with low boiling points. The reduction potentials of the group 2 metals are quite negative, just like the alkali metals. Beryllium is a large outlier though, and without it, the reduction potentials range between minus 2.92 volts to minus 2.37 volts. Beryllium is at minus 1.85 volts, so it's a bit more oxidizing than the rest of the group. And because beryllium has a much higher reduction potential and also a higher ionization energy, we will address its chemistry separately from the rest of the alkaline earth metals. Another similarity between the group 1 and group 2 metals is that the alkaline earth metals react with acids to produce cationic species and hydrogen gas, as shown here. One difference, however, is that magnesium and beryllium are not reactive enough to react with water to form hydrogen gas. The rest of the group 2 elements do display that reactivity though. Also, you should note that this reaction is not balanced, and some of the previous reactions in this slide were not balanced. Please keep that in mind and use that as practice for balancing redox reactions. I won't be mentioning this again, but if you notice certain reactions are not balanced properly, that's intentional, and that's to give you practice balancing redox reactions. Interestingly, group 2 metals can react with oxygen to form metal oxides. What this means is that the alkaline earth metals are pyrophoric and will burn in air in very exothermic reactions. You might be wondering, why doesn't magnesium spontaneously burn in air? You can actually handle magnesium turnings. The reason for this is that the magnesium oxide that forms when it reacts with air forms a passivating layer that coats the surface of the metal and prevents further reactions with air. Similarly, beryllium forms a passivating beryllium oxide layer. You can kind of think of this similar to a layer of paint coating iron, which prevents it from rusting. It's a very similar concept. Magnesium oxide and beryllium oxide are both insoluble in water, so they are stable in air. For the other alkaline earth metals, however, the oxides that they form are water soluble, so they don't form this passivating layer, and the metals will burn in air spontaneously. Even magnesium, if you remove the coating with enough energy, will burn violently, as shown in this graphic. You're probably already familiar with Grignard reagents, and their synthesis is shown below. What is not taught in organic chemistry all the time, however, is that Grignards can be fairly tricky to make. This is due to that passivating magnesium oxide layer on the surface. You often need to activate your magnesium using iodine or grinding under an inert atmosphere, etc., in order to expose the elemental metal underneath that magnesium oxide layer. What kind of reaction is this, the formation of a Grignard? This is a redox reaction, but is also a very specific type of redox reaction called an oxidative addition. We will cover these types of reactions later on in the course. Radium chemistry is a bit more limited due to its radioactivity. It has been used to treat cancer in the past, but it's being phased out for safer and more abundant radioactive atoms. For all radioactive elements, their chemistry tends to be a lot more limited because you need to follow very strict guidelines in order to research them. So we'll notice for a couple of other radioactive atoms in the main group, their chemistry is very limited, and it's for this reason. As we saw, the elemental forms of the alkaline earth metals are quite reducing. So the most common and stable oxidation state seen for group 2 is +2. Like the alkali metals, they form small localized charges in the +2 oxidation state, so they are considered hard Lewis acids. All of the group 2 metals, except beryllium, form mainly ionic compounds, the solubility of which increases as the cations get larger. Overall, though, almost all of the carbonate salts of group 2 metals are insoluble, as is magnesium hydroxide. Because magnesium hydroxide is so insoluble, it's actually a quite poor base, despite what you would initially probably have guessed. The soap scum that forms in your shower is also due to insoluble salts that form with group 2 metal cations. So these are insoluble salts that form between magnesium and calcium in your water and the fatty acid chains in your soap. Hard water has more magnesium and calcium in it, which prevents your soap from lathering and also favors the formation of soap scum. The alkaline earth metals, because they are very Lewis acidic, can be used as Lewis acid catalysts, but their general insolubility often limits their effectiveness for this application. Group 2 cations can also bind to crown ethers and cryptans, depending on their sizes. This sometimes can be used to help solubilize them in organic reactions, but it's often more convenient just to use an alkali metal. Some biological applications for group 2 metals include magnesium cations which are an important component of chlorophyll in plants. And this is located in chloroplasts and is what allows plants to undergo photosynthesis. Calcium is also important for biological systems, for forming bones, shells, etc. Another important feature of the main group are these diagonal relationships, the first of which is between lithium and magnesium. These types of diagonal relationships will come up several times during main group chemistry, and it's where elements in adjacent groups will sometimes show similar reactivity. The reason for this is that they have similar atomic and ionic radii, electronegativities, etc. This is because as you go left to right in a period, atomic radius decreases and electronegativity increases. Down a group, however, atomic radius increases and electronegativity decreases. The net result is that the elements one group over and one row down have similar properties to each other. So in this case, lithium and magnesium. Now moving on to beryllium, which behaves a little bit differently than the rest of the group 2 metals. Beryllium is extremely toxic to humans, and it has much higher ionization energies than the rest of the alkaline earth metals. As such, similar to bare protons, bare beryllium 2+ cations don't really exist under normal circumstances. This is because beryllium in the +2 oxidation state is so small and charge dense that it polarizes electron density towards itself. A consequence of this is that beryllium forms more covalent species than ionic species. Looking at beryllium chloride, the beryllium center is so positively charged that it will pull lone pair electrons from other beryllium chloride units and form dative interactions. Think of this kind of like a Lewis acid-base adduct. This happens over and over again so that beryllium chloride actually exists in infinite tetrahedral chains like this. You should note that beryllium adopts a stable electronic configuration by forming 4 covalent bonds because it has a full octet. Beryllium hydrides form similar structures, and they exist as tetrahedral chains. You're probably asking, though, how is that possible? Hydrogen in the -1 oxidation state only has 2 electrons. There are no lone pairs for dative interactions. Beryllium hydride forms 3-center 2-electron bonds, which we'll briefly look at in the next slide. A 3-center 2-electron bond is like a normal covalent bond, except there are 3 atoms interacting instead of just 2. So if you think of this 3-center 2-electron bond, where you have beryllium, a hydride, and beryllium, you have your 2 electrons being supplied by the s orbital of your hydride, and then you have overlap, like so, and the electrons from the hydride occupy all of 3 of these orbitals, one from this beryllium and one from this beryllium. What is happening here is that you have 3 orbitals overlapping, and the electrons delocalize across the whole system, keeping the atoms bound together. I know this may seem a bit strange, but as long as the orbitals have the correct energy and symmetry, they can form an interaction. When we cover MO theory, these types of interactions will probably make more sense. One way to think of it is you have 3 positively charged nuclei, and they're electrostatically held together by 2 electrons. That's another way to kind of conceptualize a 3-center 2-electron bond. Beryllium also has a diagonal relationship similar to lithium and magnesium, where beryllium and aluminum show similar reactivity and chemical properties. They have similar atomic properties for the same reasons discussed before. Both form mainly covalent interactions rather than ionic interactions because of their high charge density. And beryllium hydroxide is amphoteric rather than basic, like the other alkaline earth metals. We'll also see that aluminum hydroxide is amphoteric as well. So beryllium hydroxide can react with hydroxide in solution to form tetrahedral anionic species, which decreases the concentration of OH minus in solution. Essentially, the beryllium is acting as a Lewis acid and sequestering hydroxide. Beryllium hydroxide can also react with protic acids to form water and metal salts. So in this way, it can act as an acid or a base. Hydrated beryllium 2+ is acidic with a similar pH, 5.4 versus 5, to hydrated aluminum 3+. Why do you think that hydrated beryllium is so acidic? The reason is that the beryllium is so small and charge dense in the +2 oxidation state that it pulls the electron density away from the bound water molecules, which weakens the OH bonds and makes the water more acidic. Why aren't the other hydrated alkaline earth metals as acidic? The other alkaline earth metals aren't as charge dense, so they can't polarize electron density towards themselves as strongly as beryllium, and they don't show this type of chemistry. Aluminum, however, does, hence the diagonal relationship.
This concludes today's lecture. If anything was unclear, please feel free to ask questions during office hours or try rereading the textbook to clarify concepts. And as always, there are some useful websites and resources in the links below to help with understanding some of the concepts that were presented today.